Welcome back again to part 22. This video is the first of 4 that will provide more detail on the backward perturbation risk model. That is, there will be less computing and more modeling. The mathematical notation and ideas are a step up. There is a lot on the screen that will not be verbalized, though if you want to understand everything, stopping the video occasionally is your best method. Or, if you're more ambitious, you could download the video transcript from the series website and study the transcript. One goal is to define perturbation alpha. Perturbation alpha will play the same structural role as CAPM alpha does in the equation for CAPM, but its interpretation is quite different. For instance, in CAPM, alpha is a constant that is estimated by OLS. In PRM, perturbation alpha is a random variable. More on that in video 25. Previously, it was noted that expected Sharpe ratios for the low and high CAPM beta portfolios are equal under full condition 6. Let's assume a computational convenience. The expected low perturbation in period t given the market perturbation in period t equals the low ideal beta times the market perturbation. It will turn out that this is not a correct conditional expectation, but it's close and will help for a while. With the conditional expectation of equation 22.1, we have the expected total return of the low CAPM beta portfolio in period t given the market perturbation minus the risk-free rate equals the low ideal beta times the excess return of the market. You can follow the algebra. With the result that where, like most expectations, it's not usually realized. If the degree to which it does not hold in a given time period is called h, then the low perturbation in period t equals the sum of the low ideal beta plus the low h multiplied by the market perturbation. The average low perturbation equals the low ideal beta times the average market perturbation plus the average of the perturbations not explained by the market perturbations. I think this is one case where the math is easier to understand than the English describing the math. The h's add up to 0 in each time period and as an average over time, such that the weighted sum of the individual perturbations in each time period when summed and averaged across time equals the average perturbation. Where the sum of the weights is 1, and the weighted sum of the ideal betas is 1, and the weighted sum of the h's is 0 in each time period, and are therefore 0 across time, but not necessarily 0 for any given security or portfolio. Remember that the ideal beta is held constant, h is a variable, and market perturbation is a variable. Therefore, we define perturbation alpha in this manner. The low perturbation alpha equals the low h for a given time period times the market perturbation for that time period. The formula for average perturbation alpha follows immediately, where once again the weighted average alpha is 0. Note 1. The interpretation of perturbation alpha is more subtle in the PRM than the interpretation of alpha in CAPM. If the market perturbation is positive in a given time period, then a positive h means greater return from the perturbation. If the market perturbation is negative in a given time period, then a positive h means lesser return from the perturbation. If h is typically positive for a given asset or portfolio over many time periods, it means higher standard deviation without higher arithmetic average return. Note 2. The perturbations might or might not sum to 0 in any time period or across time periods, but the perturbation alphas necessarily sum to 0 in each time period. Note 3. It is likely that the average perturbation is approximately 0 over time, while the average low perturbation alpha equals minus the average high perturbation alpha, which does not equal 0. However, the modeling to this point has been largely based on an average perturbation equal to 0, and the perturbation alphas also equal to 0. However, it is likely that the average perturbation alphas are only approximately equal to 0. Note 4. It is the perturbations themselves that are the excess risk-adjusted returns, not the alphas, although the alphas are part of the perturbations. Note 5. In the PRM, it is possible that all portfolios and the market itself will have excess risk-adjusted return or deficient risk-adjusted return. That is, the market might be considered too high or too low. Note 6. By setting the correlation between perturbations equal to 1, and by setting the individual perturbations equal to the ideal beta times the market perturbation, CAPM beta will equal ideal beta, CAPM alphas will equal 0, all Sharpe ratios will be equal, and there will be 0 idiosyncratic risk. I should prove this. Proof of Note 6. Here is the PRM decomposition of the low CAPM beta with the covariance term expanded. If the correlation of the perturbations equals 1, then the low h is a constant and the correlation term drops out of the PRM decomposition. Since the correlation of the perturbations is 1, and by assumption the individual perturbation risks are equal to the ideal beta times the market perturbation risk, which if the low h is a constant, then that constant is 0 for all t. Then substituting the individual ideal betas times the market perturbation risk for individual perturbation risks, and factoring. And factoring again, simplifying, canceling, factoring yet again, and canceling. Therefore, CAPM beta equals ideal beta given that the correlation between perturbations equals 1. The low ideal beta times the standard deviation of the perturbations of the market is equal to the standard deviation of the low perturbations, and the high ideal beta times the standard deviation of the market perturbations is equal to the standard deviation of the high perturbations. Furthermore, since the low CAPM beta equals the low ideal beta, then the expected CAPM alphas are 0. If the expected CAPM alphas are 0, then full condition 4 should be met. Since the Sharpe ratios are equal, full condition 6 should also be met. Superficially, full condition 4 is at odds with full condition 6. Full condition 4 is, equivalently by squaring both sides, and full condition 6 is, for both to be correct at the same time, the full perturbation risk ratio of condition 6 should be equal to the full perturbation risk ratio of condition 4. By setting them equal and expanding the covariance term, then since the correlation between perturbations is 1 and drops out, and again the individual perturbation risks equal the ideal beta times the market perturbation risk, all the market perturbation risks cancel, leaving. Therefore, when these assumptions hold, the CAPM beta will equal the ideal beta, expected CAPM alphas will be 0, Sharpe ratios will be equal, and there will be 0 idiosyncratic risk.